Hi, Savannah. We'll get started in about 5 minutes. Thanks for your patience.
Sounds good.
So give it just a minute or so more, and then we'll get started.
Okay.
All right, Savannah, I appreciate you waiting. It looks like it's gonna be the two of us. And my hope is that we can make short order of this because not to make excuses, but I've been in labor and delivery with my daughter since yesterday evening and in the hospital with her for the past week.
Well, congratulations.
Yes, congratulations is definitely a good word, and blessing and all of that, right? So,
Everything was good. Everybody's healthy.
fortunately, everybody's healthy. We had some struggles though, but everybody came.
Okay. Well, good. Congratulations.
Thank you. Like we have some additional company tonight. Well, it's usually you two anyway.
I know.
So um, so let me go ahead and share my screen because I want to give you guys the basics of what you need to have and let us all go about our way so that I can do something that looks halfway resembles sleep. All right, so I think you're seeing the course homepage, the weekly overview. And I don't know if y'all were checking your announcements, but I did kind of adjust the schedule since last Tuesday was part of fall break. And I just wanted to give you guys, the same opportunity to have a little bit of time off, just like all of the face-to-face students. So I shifted things in the weekly overview. Now I didn't move the project article deadline, which is still this Saturday. If you have not done so already, you need to get me your project articles so that I can review them and let you know if they're acceptable. And you have until Saturday at 11:59 p.m. to get that done, or it costs you 20 points. Okay. So just email the full article to me. You can send it as an attachment to my email. I'll take a look and let you know what's acceptable, and if not, why not? And then you can continue with that process if need be until 11:59 p.m. After that, I won't be approving any more articles. Okay. So that's one major thing you have on your plate. And it has been a minute, but you still have problem set 6 and 7 to do, dealing with Newton's laws. We covered that some time ago. I apologize. I might have forgotten to post the recording, but I don't think I did. But if you recall in the announcements, there is a link that says class videos from class meetings. Let's see. So the last time we met was, let's see. So we didn't meet last week. So I actually do, yeah, we didn't meet last week because of fall break. And the week before that was midterm week. So yeah, you're up to date on the videos. So, I'll add this week's video there in that same area once I get it captioned. All right, any questions so far about the project or anything like that?
Yes,
No,
ma'am.
You had a question, Savannah?
Yes, ma'am. On the app that you suggested, the AR Arvix, is that what it's called?
Yes, the app.
Are those all peer reviewed?
Yes.
Okay, that's all I needed to know because it didn't really say on any of the articles if they were peer reviewed or not. So as long as they meet the 15 and it's one of the topics, then that should be good.
Right. So, and long enough, right? Long enough also.
Yeah.
The R-Active and Hindawi only offer peer-reviewed articles. If you use the library databases, though, you might have to do a little bit of filtering to get it to spit back only peer-reviewed articles. But Hindawi and the app, that's all you have access to.
Okay, awesome. Thank you.
No problem. All right, so so you've got to get your article approved by this weekend. Also, problem set 6 and 7, both of those deal with Newton's laws, which is like a couple of weeks back that we covered that. And then, of course, you'll have a discussion dealing with tonight's topic, okay? To help you with that, you have access to chapter 6 in the textbook. There's a nice set of videos and some additional notes. So I'm gonna go very quickly through the supplemental notes. And what I'm gonna focus on is the basics of what, the most important things, okay? And then what I would ask is that while you're working this weekend, if you have any questions, reach out to me. I'm happy to help, okay? That way I can get us all out of here before I fall asleep on you. All right. So this week we're dealing with gravitation. The whole idea is that gravity is a little bit more complicated than what we have looked at so far. If you recall, we talked about acceleration for gravity, especially on planet Earth, 9.8 meters per second squared down. And we've talked about gravity as it produces weight on an object by pulling on it, right? So weight is the force of gravity on an object. But what we haven't looked at is what specifically describes the force of gravity, right? How does it behave if we look at it from the perspective of the universe, not just on planet Earth, okay? And so to help us understand that, thanks to Newton, we have the universal law of gravitation. And you can see here that the idea is that if you pick any two particles in the whole universe, we can find the force between them by looking at the product of their masses divided by the square of the distance between them. So that formula that you see there allows you to figure out the force of gravity between any two objects in the universe. And all you need to know is their masses, how far apart they are, and this gravitational constant, big G. Now, we've looked at gravity from the perspective of little g, which is an acceleration. And that acceleration changes from place to place. But when you're using Newton's universal law of gravitation, you have to remember that big G is a constant, and it is the same no matter where you go in the universe, okay? And this, you'll see some examples mentioned here. The reason we have tides is because of the gravitational force between the Earth and the Moon. That's like a phenomenon that's happening in your environment all the time as it relates to this idea of the universal nature of gravity. Weightlessness, we see a lot these days about astronauts and space flights. And one of the phenomena that you typically see when they show astronauts in outer space is that idea that they're able to move around so freely, right? But don't take that to mean that because they can move so freely, there's no gravity. In fact, there's gravity everywhere in the universe. And this idea of weightlessness is just a sensation that people, you might feel temporarily because you might be moving in an object that is free falling. Okay. So if an object is free falling and you're inside the object that's free falling, you're going to experience what's called the sensation of weightlessness. Okay. And then the other thing is this idea of microgravity. And so we talk about microgravity being the small accelerations that objects experience when they're in kind of a rotating environment. They're they're attributing a small amount of gravity to non-gravitational forces. And so that's why it's called microgravity. But don't ever take the perspective that there's no gravity in outer space. There's gravity everywhere in the universe. Okay. Of course, another important phenomena that can be explained by understanding gravity is the motion of the planets, right? And this kind of gives a little bit of a history lesson, showing that, you know, all the way back to the ancient Greeks and before, we've always had a curiosity about the movement of the planets. But it wasn't until Kepler came along that we really had some laws, you know, some real solid explanation of the motion of the planets. Prior to Kepler, you know, we had an idea that in thinking that the Earth was the center of our solar system. But over time, we abandoned this Earth-centered notion of our solar system and moved toward a heliocentric view. Heliocentric meaning the sun at the center. And we attribute our understanding of that, what started with Ptolemy and other folks, but ultimately it was Kepler who solidified our understanding of that, and some others. They mentioned Tycho Brahe, who was also important in formulating that understanding. But it was really and truly Kepler's work that Newton built on to help understand gravitation.
I have a quick question. So like with the model of the moon and Earth showing that gravity is what makes the tides, why in like lakes, big lakes, does it affect it the same way, or is it just ocean?
Oh, well, you know, the idea of water, right? Water. So they just gave that as an example there.
Okay.
Like, yeah, when they say oceans, it's, I mean, you think about it, if you live near a lake or something like that, you know, they talk about often about high tide, low tide, that kind of thing. Right?
So that's related to,
it's the pull of the, it's the pull that the moon exerts on the water, right?
Gotcha.
Yeah. Okay. So now, kind of getting back, while I don't really go into a lot of great depth on Kepler's laws, the one that I want you to focus on the most is actually the third law. Okay. There are 3 laws. Kepler came up with 3 laws to explain planetary motion. And the one that we focus on the most is the third law. And not that we really get deep into using it, but the reason I focus on that is because it talks about the relationship between the period of a planet's orbit to the orbit radius. Okay. And if you recall, when we talked about circular motion, we talked about the period and the orbit radius. And so this relationship between the period and the orbit radius was what Newton used to solidify his understanding of gravity in a mathematical way, right? That formula that we use, the universal law of gravitation, can be derived right out of this, you know, out of Kepler's laws, using Kepler's law. And it was like a real, it was kind of one of the linchpins, you know, that led Newton to realize that he was really on to something when he was trying to explain, you know, this force of gravity that makes apples fall, for example, on planet Earth. You know, the story that apple falls, hits him in the head, he wakes up, says, voila, right? Gravity. Well, not quite. There's a lot of number crunching and using Kepler's laws before he actually got to that point. But what he didn't realize was that, you know, by using Kepler's laws, he could come up with a more solid and accurate explanation of the force of gravity. So that's the background. Honestly and truthfully, is this formula. This formula is the universal law of gravitation. And much of what you'll be looking at in the discussion and in the problem set centers on using this formula and understanding the relationship between the variables in this formula. So let me show you some resources that can really help you with that, okay? So if you go under the announcements and into our extra notes folder, recall we have some extra resources, and click on that link. And then if you go into gravitation notes, okay.
Now you can sit up and be comfortable.
Hopefully. And let me just stop the share for just a moment. I'm sure I see the hand raised on the iPhone. I apologize. I can't see your hands raised when I'm sharing the screen. So if you have a question, just feel free to unmute and ask your question.
It's been up the whole time, so I don't.
Okay. Oh, again, I can't see it when I'm sharing, so I wasn't aware, you know, when it went up. I just thought maybe something that I had covered here just a moment ago wasn't clear. So, you know, I wanted to make sure.
I think when he joins, it comes up, and it stays there.
Make sure that you're not waiting.
Yeah. But I just wanted to give you guys a heads up. If you hear some voices in the background, it's because I'm at the hospital still with my daughter. She just delivered maybe about 3 hours ago at the most, and we're in ICU with her right now. So I did not want to cancel class, but by the same token, as I mentioned, I've been at this for about a week now with very minimal sleep. So, you know, I wanted to give you guys some resources and some background so that you can function and deal with this week's material. Of course, you know that I'm always a resource for you. You can reach out to me by email, come do an office hours if you need to, and I'll be more than happy to answer any questions that you might be having. So with that, let me go ahead and I'll share the screen again. So when I went into the extra resources, I just clicked on the folder that says gravitation. And let me put it in this view, okay? So in here, one of the most important things you want to come and take a look at are these two examples here, example 1 and 2, okay? Because they both show you in detail how to utilize the gravitation formula, okay? You can see from this example, the value of big G in the formula, which is extremely small, you see, times 10 to the minus 11. That's why we typically say that gravity is the weaker of all of the 4 fundamental forces that I mentioned those to you a couple of weeks back when I covered Newton's laws. Gravity is the weakest of the 4 fundamental forces. And that's because if you look at the value of the gravitation constant, it's extremely small, 10 to the minus 11. Okay, so it means you're going to have some very large objects like the Earth, for example, before you really feel the effect of the gravitation force. So you can see how we use the formula, for example, when we want to know the force of gravity between a student that's standing at sea level. The student is 70 kilograms, but you can see how big the earth is, quite large. And so when using this formula, my advice to you is make your substitutions in the formula first, then use your calculator to work out the value of the numbers, and then use the rules for exponents to work out the exponents. Don't mix the numbers and the exponents, because unless you're very comfortable with your fancy calculator, it's going to give you the wrong answer, okay? If you don't group things correctly, it'll give you the wrong answer. So I always do it the old-fashioned way. I write out my formula, I substitute the values, and then I do the numbers, and then I do the exponents, and then I put them back together. Okay, so that's how they got 686 newtons. From the numbers, you get 68.6. From the exponents, you get 10 to the 1. That becomes 686 newtons. Now, one of the key things that I want you to know about gravitation is that when you're on planet Earth, the force of gravitation is equivalent to your weight. So if we take the mass of this student that's standing on the Earth and multiply their mass times the acceleration due to gravity, we'll get the same 686 newtons. Okay, so you might be thinking, well, if you're going to get the same thing just by doing W equals mg, why wouldn't you continue doing that all the time? Because that's a much easier formula. Well, example 2 shows you why not. Because in example 2, this student is not standing on planet Earth. They're flying in a jet 40,000 feet above the Earth. And you can see that the process is still the same. You substitute value for big G, the value for the mass of the Earth, the value for the mass of the student. But this time, since the student is not standing at sea level, you have to substitute in the actual distance from the center of the Earth. And that is, in this case, 40,000 feet more than when they were standing at sea level. Well, if you go through the process, separate out your numbers, separate out your exponents, you'll get 68.4 from the numbers and the same 10 to the 1 for the exponent. But this time, the force of gravity becomes 684 newtons. See, that's the beauty of Newton's law of gravitation. If you're not standing on the planet, you can't use W equals mg. You have to use the universal law of gravitation to figure out how much is the Earth pulling on this student that's flying 40,000 feet above the Earth in a jet or airplane. Okay, so the universal law of gravitation allows you to find that force of attraction between any two objects if you know their mass and how far apart they are. If one of those objects happens to be the Earth and the other one happens to be on the Earth, then that's equivalent. That force of gravitation is equivalent to the object's weight. But if it's not on the planet, you can't use the weight formula, W equals mg. You have to go to the gravitation formula. Okay. So those are two really good examples to show you how to use the formula. And then the other thing that I've made available to you are a nice set of links that you can use to, just if you want to watch some videos and do some reading about gravitation in terms of how did Newton come up with the actual formula. Some of these links will help you to get an insight into that, especially the one dealing with the inverse square law. Okay. By the way, these links and information is also very useful to do the problem set that goes along with gravitation, problem set 8. The other things that I have for you here is a way of looking at the connection between circular motion and gravitation motion. So especially if we're looking at orbit motion, right? one of the things we looked at for circular motion, we were particularly interested in was satellites. And those satellites are in orbit around the Earth. Well, the question is, well, what's keeping them in orbit? Well, gravity. Well, so that means we have two ways that we could look at this motion. We could look at it from our circular motion formulas, where we find the speed and the centripetal acceleration. And then we can take it a step further and now add Newton's second law, F equals ma. Or we can go over here and look at it from the perspective of gravitation. So in other words, we have two ways that we can find the speed. Our old circular motion formula or utilizing gravitation. We can find acceleration using the centripetal acceleration formula or our new gravitation formula. And then finally, the important thing, if I mentioned to you before, right out of Kepler's law, is the relationship between the period and the orbit radius. And that is the period squared is proportional to the orbit radius cubed, okay? So you have some good information in these extra notes. My suggestion to you is use them to help you with the discussion questions, and also use this to help you with the problem set 8 that won't actually be due until next week, okay? So these other screenshots are basically just a summary of Newton's universal law of gravitation, okay? So giving you a little bit insight into the formula. What's the value of big G? What units are you using when you're finding this force? And then the idea of an inverse square law that says this gravitation force is proportional to 1 over the distance squared. Inverse square law. In fact, quite a few things in nature obey an inverse square law. And then I explained to you the difference between big G and little g. Okay. And then I explained what are the values, what are the variables that are in the, that are a part of the gravitation formula. Okay. So I think if you invest some time to look at these resources here under the extra notes resources, that will definitely help you to deal with problem set number 8 and this week's discussion. Okay. So with that, I'm going to stop the share and ask before we close shop today, do you have any questions for me? All right. So if you don't have any questions, I'm going to go ahead and stop today's recording.